So in this section, we will discuss electric potential difference. So in order to understand this topic, what we consider is, we'll consider a point source charge to be located at the origin, right? And due to this point positive source charge, the electric field lines will be in the radially outward direction. So I am drawing the electric field lines only in the first quadrant, like this. These lines represent the electric field lines. Due to an isolated source charge, which is point, the electric field is spherically symmetrical. This is the electric field. Let us consider any two points, suppose point A and point B, to be under the influence of electric field due to this source charge. Let the position vector of point A be RA, while the position vector of point B be RB. These are the position vectors. And also let us consider this to be any arbitrary path, AB be any arbitrary path. And also let P be any arbitrary point P on this path. PQ is any small elementary portion. Let us consider it by DL, right? So at point P, the electric field is directed in the outward direction. Now what we assume is, let us consider a point charge Q0 to be placed at point P. This is a test charge. This positive test charge under the influence of this positive source charge will experience an electric force in the away direction, that is along the direction of the electric field, and that electric force experience would be Q0 E. Now as per the definition of potential difference, the potential difference, it is the difference in the potential between the 2 points, right? So the potential difference between the 2 points A and B is defined as work done per unit charge in moving this charge between these 2 points without any acceleration. Without any acceleration means this charge Q0 is to be moved along any arbitrary path with net force acting on the charge should be 0. So that is why charge Q0 is to be moved from A to B without any acceleration. So let's first concentrate upon its definition part, and then we'll try to get its relationship with the line integral electric field, and then obviously we'll obtain the expression for the potential difference as well, right? So by definition, potential difference between the points A and B. A is the initial point, B is the final point. So potential at point B minus potential at point A. Difference, final minus initial. So the potential difference between the 2 points A and B is defined as work done per unit charge. This charge is to be moved from one point to another. So potential difference between the 2 points is defined as work done per unit charge in moving this charge between these 2 points without any acceleration. So this is the definition of potential difference. In order to obtain the expression, we need to find out the total work done required to move this charge Q0 from point A to point B. And in order to find out the total amount of work done, we first calculate the small amount of work done in moving the charge Q0 from P to Q through small distance dl, right, without any acceleration. So, small amount of work done in moving this charge Q0 from P to Q is given by scalar product of force and displacement. So it would be scalar product of force and displacement. Now look, always remember this charge Q0 is to be moved along the path AB without any acceleration. So the net force acting on charge Q0 should be 0. If this charge is left alone over here, it will experience a force along this direction. So in order to balance this force, the force which is to be applied should be in a direction opposite to that of the electric field. This force applied should be of same magnitude as that of this electric force, but it should be directed opposite to that of the electric field, so that the net force at point Q0 becomes 0, right? So therefore, F vector, it is the applied force. It should be applied in a direction opposite to that of the electric field, so that it balances this force, so that the net force becomes 0. And it is only in this case that the charge can be moved along any arbitrary path without any acceleration. So it should be minus Q0. This is very important. Minus sign indicates that the force is to be applied in a direction opposite to that of the electric field. Dot dl vector. This is a small work done. So if we integrate it, we can obtain the expression of the total work done. So on integrating, we get total work done. Q naught can be taken on the left hand side. So we get negative of E vector dot dl vector. Integration of this. And limits will be from RA to RB, from point A to point B. Now, consider these two equations. So from 1 and 2, we conclude that, potential difference is numerically equal to the negative of the line integral of the electric field between the two given points, which in this case is A and B. So this is a very, very important expression. And this gives the relationship between the potential difference and the line integral of electric field. So what we have derived is potential difference between the 2 points A and B is numerically equal to the negative of the line integral of the electric field between the 2 points. So put this as equation number 3. Now using the previous obtained expression for the line integral of electric field, we can very much make use in finding the expression for the potential difference. So let's see. As we know, this we have done in the previous article, line integral of the electric field, limits RA to RB, it's given by Q over 4 pi epsilon 1 by RA minus 1 by RB. Put this as equation number 4. Now we can compare equation 3 and 4. So therefore, from equation 3 and 4, we conclude that potential difference between the 2 points A and B, A is the initial point, B is the final point. So potential difference is the difference in the potential between those 2 points. Final potential minus initial potential at point A. So potential difference should be equal to, just equate these two. This is negative sign. So in order to compensate the negative sign, these two terms can be interchanged. So what we get is Q over 4 pi epsilon 1 by RB minus 1 by RA. This is the expression for the potential difference. And if you further expand it, the potential at point B, it will be given by Q over 4 pi epsilon RB, while the potential at point A, it is given by Q over 4 pi epsilon RA. These are the expressions for the potential at point A and point B respectively. We will derive it in the separate section as well. Now let's discuss the SI unit of potential difference. One more thing before we discuss the SI unit, again a very, very important concept. Potential difference is a scalar quantity. Work done is a scalar quantity, charge is a scalar quantity. Therefore potential difference or electric potential is a scalar quantity having only magnitude but no direction. Let's define it. The SI unit of potential difference is volt. The SI unit of work is joule. The SI unit of charge is coulomb. So the potential difference between the 2 points is said to be 1 volt when 1 joule of work is required to be done in moving this charge of 1 coulomb between those 2 points without any acceleration. So this is how the SI unit of potential difference, which is volt, can be defined. Now regarding its dimensional formula, kg in terms of basic units can be written as kg meter square per second square, while coulomb it's ampere second. So in fundamental units it would be kg meter square s to the power minus 3 a to the power minus 1. Therefore dimensional formula for potential or potential difference would be m L2 t minus 3 a minus 1. This is the dimensional formula for the potential difference. Now we will discuss some other units of potential and potential difference as well. As I told you earlier, in CGS there are 2 units. One is the electrostatic unit and the other is the EMU, which is the electromagnetic unit. So let's discuss those units as well. So in the CGS system, there are two units. One is the electrostatic unit, the other one is the electromagnetic unit. The electrostatic CGS unit of potential difference is stat volt, while the electromagnetic CGS unit of potential difference is ab volt. So we can easily find the relationship between stat volt and volt. How to proceed is like we will change this SI system into CGS system. So for that, what to do is 1 volt is equal to 1 joule is 10 to the 7 erg. 1 coulomb, I've stated in the earlier section, 1 coulomb is 3 into 10 to the power 9 stat coulomb. So what we get is 1 volt is equal to 1 by 3 into 10 to the 2, which is 300 erg divided by stat coulomb. Erg divided by stat coulomb is stat volt. This is the relationship between the SI and the ESU CGS unit of potential difference. In the similar manner, we can get the relationship between the SI and the electromagnetic CGS unit of potential difference. So we'll proceed in the similar manner. 1 volt can also be written as 1 joule, it is 10 to the 7 erg. 1 coulomb, its electromagnetic unit is ab coulomb, and 1 coulomb is 1 by 10 ab coulomb. So what we get is 1 volt is equal to 10 raised to the power 8 erg divided by ab coulomb. That will give us ab volt. So this is the relationship between the SI unit of potential difference and the electromagnetic CGS unit of